very first thing we got with exponential functions is, let's just kind of show you what we're talking about here. Is the basic setup of it is y equals b to the x. Now, if you want something more specific, we're actually looking at numbers. This would be where we have like y equals 2 to the x power. All right. So this is your basic general form over here. This is like a specific example. If we're talking about functions, again, the biggest difference is with functions is that instead of having y equals, you've got f of x equals. Just to give you a different base, maybe something like that. So this is your basic general expression we're talking about here. This would be like we actually get a specific example. Now, here's the big difference of what we're doing. The big difference from everything else we've been doing is that exponentials. Notice that in this case that your x is in the exponent. And that's the big change that we're looking at for this chapter, for this unit that we're going through, is that everything we had done before, we've been graphing, solving quadratic formula. We've been doing everything else where we had like y equals x squared, where that basically your x was your base and your power was up here that was some coefficient. Now it's kind of flip-flopping. Now x is now still not your base. Now x is in the exponent. So we're looking at like a whole new set of rules, a whole new set of things that we're doing compared to what we were doing before. And that's the big difference, is that everything we had done before now was something like that, whether it was x squared or x to the third, or x to the fourth, anything like that. X was the base and we had a number in the exponent. Now we're flip-flopping it. Now your base is a number and x is going to stay in the exponent. So when we're talking about exponential equations, that's the big difference that we're looking at, is that we're not looking at this anymore. Now we're looking at something like this where the base is an actual number that we're going through this thing. Okay, and probably the very first things you're going to have some of this is we're going to work on just some of your basics on your exponents, because I know we've done some stuff with exponents, but we're going to go back and kind of look at the basics on it. So for this one, we're going to graph y equals 2 to the x power. Okay, so what we're going to do, we're just going to walk through some numbers on this one just to make sure everybody's good with everything that's here. You'll have to do this on a few problems where you're going to have to fill in some chart and plug in some numbers. But once we get past the first section, a lot of times you're not going to have to worry about that, because we're going to basically give you some shortcuts you can work through. Okay, so we're going to start at third power, and then we'll kind of work our way down from there. Okay, so if we do y equals 2 to the third power, 2 times 2 is 4, 4 times 2 is 8. So as an ordered pair, that would be at 3, 8. If x is 2, that's 2 squared, which is 4. So it puts it 2, 4. To the first power, well, that's just 2. Okay, and a good refresher on this one. If we do 2 to the 0 power, again, think about what's happening with this one, is that every time you come down a power of 2, you're dividing it by 2 because you're taking one power off. So if you take 2 divided by 2, that should make it 1. Okay, so if we do y equals 2 to the negative 1 power, same thing. You're still going to take this number we've got and divide it by 2. So that'd be 1/2. do negative 2 power. You can take a half and divide it by 2. And if you need to do something off to the side, so you can kind of think about what we're doing there. Because that one usually everybody gets, it's when we get to this one. So if you take a half and divide it by 2, if you remember that if you do the keep it, change it, flip it, that makes it a half times a half, which makes it a fourth. Okay, now here's the thing that we want you to kind of catch and see if we're going through these. That if you notice that at 2, the answer was 4. At negative 2, the answer was 1 over 4. At 1, the answer was 2. At negative 1, the answer is 1 over 2. So basically is this one, is that if the only difference between a positive and a negative exponent, if you're going through these, is that if you take the positive answer you have and you make it a negative exponent, you can just take this answer and write it as 1 over that answer. Then again, if you've got a negative exponent, it's just the reciprocal of whatever number you had. So if you've got 2 to the negative 3 power, technically it's just 1 over 2 to the third power. So that's where we're getting that 1 over 8 that's here. So anytime you have something with a negative exponent, you can just take that negative exponent and rewrite it as 1 over whatever that expression is. So that's where we're kind of getting these answers, is that, if it was 2 squared, we know that's 4. If it's 2 to the negative 2, that's the same thing as 1 over 2 squared. So the negative just means you got to basically take the reciprocal of the answer that's there. Okay, now graph-wise, you may be saying, how are we going to graph those? Well, we'll show you, because you're not going to actually have to graph those numbers, because that would basically be almost impossible. Let's see. Okay, so go ahead and make a quick chart here. Now, on this one, we're going to kind of, just to save some room on this one, if we went 3, 8, start plotting these points, 3, 8 would be somewhere way up here. Kind of up and off the chart there. Now, the rest of them we can see. We've got 2, 4 would be here. 1, 2 would be here. 0, 1 would be there. Negative 1 and 1/2 would be there. Negative 2 and a quarter would be there. That's going to be an eighth. That's going to be a 16th. So basically, here's what it is if you go back and graph this. You're going to have a graph that will look something like that. Again, we're not going to the 3, 8 graph, the order pair for 3, 8 would be up here off the graph. Main thing is that's the basic curve that you have here. Okay, and that graph is, now you may be saying, if we graph this one, and we're going to have to graph these, online, how are we going to graph these points to know if this is accurate? You're not going to have to worry about this, because graphing those points and making it accurate, it's going to be really impossible. So it's more of one of those things that, just like when we graph, kind of flashback for a second. You know how when we graphed, if we're talking about this equation back here, when we graphed x squared, how we knew we had a basic graph like this, we'd find the vertex and maybe like one more point, and we would have that graph and go from there. We're basically going to do the same thing with this one, is that we're going to need the basic shape of it, and this is your basic shape that's here, and we're going to need like one reference point of where to kind of go through this one and how it moves, and we'll get through all the stuff for this one. So now, as you're moving through these, here's kind of the, I guess, a couple of things that you've got for this one. Everything else we've always had 0, 0 was a reference point, because if we had x to the third, if you plugged in 0, your answer was 0, correct? If you had y equals x squared, if you plugged in 0, you had 0 was the answer was here. For exponents, what happens if you plug in 0 for 2 to the 0 power? It's going to be 1, right? What happens if you do 3 to the 0 power? Also 1. What happens if you do 4 to the 0 power? Still 1, right? So no matter what you do with these, is that any number you plug in for x being 0, if it's just a basic and we don't do any shifting, no moving, no horizontal, no vertical shift, anything like that, the answer will always be at 0, 1. So 0, 1 is like our new reference point. Because it doesn't matter what number your base is. If you do anything to the 0 power, your answer is always going to be 1. So 0, 1, if we're talking about exponentials, that's your new reference point. So instead of everything going through 0, 0, 0, 1 is like our new point, our standard point that we're going to go through for this one. So if we're doing y equals b to the x, if your base is greater than 1, that's going to be your basic graph you've got here. Your base graph, your standard graph, whatever you want to talk about that thing being, that is, again, as you get close to the bottom on this part of it, it's going to get really close to 0. The answer is not quite going to be 0, but it's basically, for all intents and purposes, it's going to be 0. Same thing on this one. It's going to go, and this thing is going to start to go, and it's going to graph and run off to the top of what you're doing for those. And now, one thing that's still going to be the same when we go through these, if you've got to find the y-intercept for any of these graphs that we're going to do, you still plug in x equals 0. So that part still doesn't change because it's still an equation. If you still want to find the y-intercept, you're going to plug in x equals 0. And something that we will talk about very shortly is we're going to talk about horizontal asymptotes. That basically, for this equation that we've got here, we're going to say there's a horizontal asymptote at y equals 0, which basically means this answer is going to get really close to 0. But again, it doesn't quite get there. So basically, we're going to have a cutoff line that's going to be here. That says, okay, as long as we're doing this graph, we're never going to get below this 0 part for what's here. Because any number you plug in, as long as you're plugging something in here, it's always going to give you an answer. It's going to be just a little bit bigger than 0. So it's going to be, no matter answer-wise what we do, we're never going to quite get to 0. We'll get really close, but we'll never quite get there. And we'll talk about this more coming up in some lessons coming up pretty soon. Okay, now a couple of details that we have for this one. And you can add these basically right here. We need to talk about domain and range. That as long as we're doing y equals b to the x where the b is greater than 1, these two things will always kind of be the same for what we're looking at here. Your domain is going to be negative infinity to infinity. And your range is going to be 0 to infinity. And if they let you use a less than, greater than, in this case, this would be y would be greater than 0. Okay. And as long as the base is greater than 1, we're going to say this is going to be an exponential growth. And that's the key word on that one is that that's going to be a growth. Okay, and there's really, as far as exponentials go, we're looking at two different types. We have a growth that's here where your base is greater than 1. And then we have exponential decay. Whether that's y equals b to the x or fx b to the x, doesn't matter what it is. In that case, your base is somewhere between 0 and 1. Okay. And again, it doesn't matter what this number is. If it's still anything to 0 power, you're still going to go through 0, 1. The difference is if it's decay, then instead of the answers getting bigger, the answers are going to get smaller. This is anybody that does talks about carbon 14 dating or anything like that, that basically this point that's here, this is basically like, now one part you don't see is basically you don't see this back part of the graph back here because this doesn't make sense. But if you're doing carbon 14 dating, basically they start at this one, basically saying this is where you've got 100% of the carbon in your body. And at the time of death, you've got this part, and then it starts to go off from here. It's going to drop off and go from there. Okay. Domain and range, negative infinity to infinity. And doesn't matter what type of exponential graph you do, that this answer never changes. That a lot of times when you're going through problems, they won't even ask you about domain because the domain never changes for exponentials, whether it's growth or decay. The only thing that's going to change is your range, and that's going to change a little bit as we move from different problem to problem for this. Okay, and you can just kind of do this on the side real quick if you want to. This is kind of just like a little side note here. We graphed y equals 2 to the x power, so we had something like this. The only difference between the graphs that you get, again, this is not anything that's it's huge. You got to think about this one. Is if you have 3 to the x power, that graph is going to basically turn up just a little bit faster. Or if you had y equals 4 to the x power, it's going to turn up and just go a little bit faster. So the bigger the number you have, the faster this part of the graph is going to turn up. So if it was 1.5, it would turn up a little bit slower than 2 to the x power. all the graphs are going to look very similar. The only thing you're really going to notice is that they all still go through the point at 0, 1. But again, the bigger the base, the faster it's going to turn up. The smaller the base, as long as it stays above 1, it's going to go up just a little bit slower. But they're all going to have that same basic shape. So it's one of those things that unless you graph two things on top of each other, you'll never really see the difference because they're basically going to look the same because it's so close together as you do these. And again, this is kind of exaggerating a little bit on some of these, but if you did, 1.5, it's probably going to be almost like that. That they're all going to be really close to basically being the same graph as we go through those. So, if you just plotted a graph, that could be the graph for y equals 2 to the x, that could be 3 to the x, that could be 4 to the x. So if you just did a quick sketch of it, that's the same graph for anything where the base is bigger than 1. You just won't be able to tell it unless you compare it to another graph that's there. Okay. All right, now here's where we start making some changes, doing some different things with these. And this will actually be really good review. Because again, at this point, we're less than 3 weeks away. We're probably like 2.5 weeks from final exams. So this will actually be a really good review because it's going back to, think about when we did transformations of like x squared. That if we did x plus, and again, you don't write this part down. This is just kind of scribbling here. If you had x plus 1 squared, if you had this graph and this graph, what did this plus 1 on the inside do to this graph? Moved it one space to the, there we go. Remember, anything on the inside makes it go horizontal. Anything on the outside is your vertical. That's your up and down. And as far as this goes with these transformations for exponentials, it's still the exact same thing. Where that number is tells you what the graph is going to do. If it's inside the parentheses, you're going to move it left and right. If it's outside the parentheses, you're going to move it up and down. The big difference is for this one, when we talk about transformations, is we've got this, that basically we're looking at it being either inside the exponent or outside of the exponent. So in this case, we're going to do one on the inside. And again, that's the one thing we've been trying to get you to see is that whether we did exponents, whether we did quadratics, whether we did absolute values, whether we did fill in the blank, anything, it's always that same thing. Anything on the inside makes it go. Now, in this case, it's not a parentheses in this case. It's more of it's on the inside of the exponent. Or just inside the exponent, sorry. It's going to move the graph opposite horizontally. So it's still that exact same thing. You're still going to move it horizontally, but you're going to move it in the opposite direction. Okay, so again, you got some number, and it should, and again, I'm not trying to trick you on these. It should be really obvious whether or not they're putting something in the exponent or outside the exponent. If it's not real obvious, let me know. We'll make sure that you understand what's going on with it. So if you add or subtract something on the outside, it moves the graph vertically. So inside is opposite horizontal, outside is still vertical. So it's still the exact same thing that we were doing before. It's just now it's a different graph. And again, that works whether it's exponents, exponentials. That doesn't matter if it's quadratics. That doesn't matter if it's absolute values. Basically, everything we've kind of done so far, it's always the same thing. Anything on the inside is opposite horizontal direction. Anything on the outside is going to be a vertical direction. And that pretty much holds true for almost every graph that you're going to do, even up through pre-cal as you go through those. Okay, now what about the negatives? We got because you'll get some negative numbers in front that will throw some things off. So if you have a negative in front of the base, so if you have something like that where you got negative 2 to the x power, that causes a reflection about the x-axis. Then again, it's still on the outside because if you do that negative is not in the exponent, it's outside the exponent. That's basically the same thing we're doing here. It's going to be vertical where we go up and down over the x-axis. So that's where you're going to flip a graph up or down, that kind of way. And then if you multiply by a number, and if that number is greater than 1, think about when we did the quadratics. If you're the bigger the number you multiplied, how you stretched your hands apart. Same thing on this one. If the number is greater than 1, it stretches the graph. And if the number is less than 1, it compresses the graph. Okay, now, and this was something that we figured out that if you're getting ready for pre-cal next year, which a lot of y'all probably are, when they talk about stretching and compressing, they kind of switch gears in pre-cal when they talk about this one, that whether you talk about a stretch or a compress, remember that is still a dilation. So sometimes, because you think about your eyes when if you go to the eye doctor, you get your eyes dilated where your pupils get a lot bigger. Same thing on this one. That anytime you're doing these, you're basically you're stretching or compressing those. You're doing dilations on your eyes as you go through that. So. Okay, so what we're going to do just a few examples of some problems where you're going to have to do some graphs, do some stretches, tell me kind of what's going on with it. And if we've got time, we'll show you some other problems that you can see with money that would kind of tie on this one, but we might have to save those for another day just because we may get started a little bit late. Okay, so what we're going to do, let's graph y equals 3 to the x minus 4. And we're also going to describe how it compares to y equals 3 to the x power. Okay, and then one other easy question that they'll throw at you, and we'll practice on this a little bit too. They're going to ask you, is this a growth, exponential growth, or is it exponential decay? Okay, so in this case, your base is 3. And growth or decay depends on what your base is. In this case, your base is bigger than 1, so it makes it growth. Decay, again, if it's decay, it's somewhere between 0 and 1. It's going to be some kind of fractional answer that's less than 1, but also still greater than 0 at the same point. Okay, and then what we're going to do is we're going to kind of do a rough sketch of it here. So if we were graphing y equals 3 to the x power, this is 1. Actually, let me scoot this down just a little bit. Get one more spot underneath it here. Okay, so just to kind of get an idea of this one, if we've got y equals 3 to the x power, if we were just graphing that one, it would be one that would look kind of like this, and just kind of doing it dashed so we can see what this would be. So that would be 3 to the x, it would look something like that. And this is where, again, y'all aren't going to have to graph like 10,000 specific points on these. Now, they still may make you make a list over here, make a chart, and go back and plug in some values just to play around with it and see what you can come up with. But I'm not going to make you do a lot of that. They're going to make you do that just to practice it a little bit. And they should give you some numbers to plug in. If not, you can pick some numbers and plug it in. But the main thing is, in this case, if you've got a -4 that's here, that -4 means we're going to take this graph and we're going to move it 4 spaces to the right. So if we had 3 to the x, which is this graph, if it's 3 to the x minus 4, we're going to move it 4 spaces to the right. So all we're going to do is take this graph we've got here, and instead of being at 0, 1, we're just going to move it over 1, 2, 3, 4 spaces, and that's going to put it there. So that would be the actual graph of 3 to the x minus 4. Okay, so again, all we did was we took this graph and just scooted everything over 4 spaces this way and just moved that same graph we've got there. If it did ask you for what's the y-intercept, again, you would plug in 0 here, so it'd be 3 to the 0 minus 4, which would be 3 to the -4 power. So that would be 1 over 3 to the 4th power, which would be 1 over 81. I don't know if they would ask you to do that. It's possible. Or they may make you take that and turn that back into a decimal number. Possibly. So again, if you went back and got that, that would be almost, it'd be like 0.019 something or other like that. So it's a really small number if we're looking at that part. Okay, we'll keep talking about domain and range because we need to at least keep talking about those a little bit. Again, if we're talking about exponentials, this part never changes. Domain is still -infinity to infinity. Okay, your range is your up and down movement. We did not move this graph any up or down. We just moved it side to side. So the range is still going to be 0 to infinity. Or again, if they let you use the inequality symbols, that's just y greater than 0. Okay, and we asked, when we're talking about how does it compare, We set it basically back here that we moved it 4 spaces to the right. So when they're asking about comparisons, that's what they're asking for. Is it up, down, left, or right? What did you do? Did you reflect it? Did you stretch it? Did you shrink it? Did you compress it? That kind of thing. Okay, so for the next two, let's just do this. Instead of graphing these, let's just describe the movements here. Okay, so we're not going to graph this one just to kind of speed things up a little bit. So there's our function. We've got f of x is negative 1/2, 1/3 x. How does that compare to f of x equals 1/3 x? And probably a lot of times in that case, it didn't do a good job of this. One of these should be g of x. The other one should be f of x. I'll do that on the next one. Usually they don't give it to the same function. So usually they'll call this, like g of x or something like that. Okay, so first thing is you've got, in this case, your base is 1/3. So that means that this is a decay. Okay, so that takes care of that part that's here, which is this part we got here. Now we got to worry about the negative 1/2. Negative that's here, that means it's a reflection. About the x-axis. And then the 1/2, say compress, they might say shrink. Scale of a half. Or they'll say something about a scalar of something about, they'll mention that it's 1/2 that we're kind of using for that part. Which again means it's going to flatten this thing out a little bit. It's not going to be as steep as it normally would be, so it would be a little bit flatter. Okay, one more of these where we just kind of describe the movements of it, and we'll show you a few other little things here. Okay, so let's do 3 times 4 to the x plus 3 minus 1. And how does that compare to 4 to the x power? Okay, so there's the base that we've got here. So basically you kind of take that part out, and whatever's left over, you got to describe those pieces. So we've got the 3 that's here. So it's a stretch of 3. Again, sometimes we're thinking about pre-cal. Pre-cal, they use the word dilation a lot. So remember, stretch or shrink, it's still dilation. The plus 3 that's on the inside of the exponent, that should go 3 the opposite direction, so that's 3 to the left. The negative 1 that's on the outside means that's your vertical, so that should go 1 down. Okay, so same thing we've been doing with all the other stuff. It's still the same, some number in front. Anything bigger than 1, it's a stretch. Anything less than 1, it's a shrink or a compress. Still dilation, whichever way we talk about it there. Anything on the inside is left and right. Anything on the outside of the exponent, that's an up or a down. Okay, let's do this. Do this on the next page. About to run out of room on this one, so we'll go to the next page for the next example. Okay, so two things on this one. First thing we'll do, we're going to identify it either as a growth or decay. And then after we do that, we're going to find out what the y-intercept is going to be. Okay, so we'll start off with y equals 0.95x. All right, again, your base is 0.95, so that means it's less than 1, so that's decay. Again, for the y-intercept, plug that in. And as long as it's just the base to a number, that's anything to the 0 power, that's still just 1. So your y-intercept would be at 0, 1. All right, now somebody might be thinking, well, if you plug in 0 and the answer is always 1, won't the y-intercept always be at 0, 1? Not necessarily, because you remember the problem we had back here when we did this one. This y-intercept was at 0 and then 1 over 81 because we wound up moving it left and right. So if you wind up doing some transformation stuff, the answer may not necessarily be at 0, 1. The initial part of it might be that way, but then when you move some things around, it might actually change it just a little bit. So let's say it's 0.5 times 3 to the x power. Okay, so in this case, your base is 3. So that's growth. Okay, if you plug in 0, you do still get 1 for this part. It's still 3 to the 0 power, which is 1, but then you're going to multiply that by half, which means in that case it's going to be 0.5. So for that one, your y-intercept would be at 0 and then 0.5 or a half. So again, you still got the initial, okay, you're still going to have something to the 0 power, which will be 1, but then you may add, subtract, multiply, you may move some stuff around based on some other transformations, some scale factors, some dilations, may change this thing so that it's not always going to be at 0, 1, because you are going to transform it some way, shape, or another with some different properties and different things that you may go with there. Okay, we've got, let me get you this one formula. I don't know if we got two formulas to actually look at. I don't know if we can get both of them in. We'll get one today. We may have to add one on tomorrow, but if we do, that'll be fine. Yeah. Now, and there's all kinds of different growth and decay formulas that's out there. There's for every formula, there's one that fits in a certain specific way for certain specific ones. But as far as like just a general basic idea of it, this is kind of where they all start. And then once you get this one, then again, you can tweak it, change it, adjust it a little bit because depending on what you do, everyone's got a little different one. But as far as just a basic growth or decay formula. This is as basic as it gets. Again, you can tweak and adjust it for different specific models for different things, but this is just like the basic idea of what we're looking at. Okay, so the lowercase a in this case, which is this one that's here, that's your starting amount. R, which is pretty universal, that's your rate. The one thing is you have to change it to a decimal because a lot of times you're going to get it in percent. You've got to rewrite it as a decimal. T is time, pretty standard on that one. And then the capital A of T is the amount after T time. Okay, and most of the questions on this one, they will take this back to money, which is kind of the easy thing to do in this case. So a lot of times what to do for this one, and again, if this is just basic general, a lot of times if we're talking about money, they change this A to a P where this is P is principal. It's still your starting amount. They just talk about it in money terms. But we'll go ahead and do this one as far as money goes. So let's say if you have $7,000 to invest for, I don't know, 20 years. Maybe somebody left you a trust fund and they're saying, all right, we're going to make it sit for 20 years. Maybe it was one of those that you've got a grandparent, uncle, aunt, somebody in the family that said, all right, we're going to give you some money when you're born, but it's got to sit there for 20 years so that you can't touch it till you turn 20, sometime in college or if you're working, whatever you're going to do. They give you 20 years. This $7,000 is going to sit for 20 years, and some bank somewhere may lock in a interest rate. Let's say maybe say it's 4%. Basically, they're going to say, all right, how much money will you have? Okay, so they gave us $7,000. That's our A. And again, if we're talking about money, sometimes they use P. Still the starting amount. Your time is 20 years. And your rate in this case is 4%. But again, you've got to rewrite that as a decimal. So you always have to move that over two places. So that would be at 0.04. Okay, now here's where you get calculator practice. Because if you plug in those numbers, the amount of time, that's a, basically that would be A of 20. Because after 20 years, we don't know what this amount's going to be. It's $7,000 times 1 plus 0.04 raised to the 20th power. And if you've got a good enough calculator, you can pretty much take that amount that you have and punch it straight in, just like that, and let it do what it's got to do. And again, a lot of that's just knowing what to do with your calculator and how to get there. So the ones that's at board, 7,000, do your parentheses. It's 1 plus 0.04. And then we're going to raise that to the 20th power. Okay. So if you had somebody in your family that was nice enough to give you 7,000, but they said, we're going to make it sit for a little while, at 4%, if you let it sit for 20 years, that's going to be $15,337.86. So basically, you double your money there.